Okay, welcome everyone. Thank you so much for joining us at an unusual time. Ivana is going to be talking about tensor category KLK SL2N via minimal affine W-algebras at the non-admissible level K minus 2n plus 1 over 2. Feel free to start when you're ready.
Okay, thank you very much for the introduction, and I would like to thank the organizers for inviting me. It's my great pleasure to give a talk here. Okay, so my talk is on the tensor category KLK SL2N via minimal affine W-algebras at non-admissible level K minus 2n plus 1 halves. This talk is joint work with Dražen Adamović, Tomas Krucig, and Ozren Pershen. The results from this talk could be found in our two papers. The first one is on the representation theory of simple affine VOA associated to SL4 at level minus 5 halves. And in other paper, we extend some of these results to the whole series SL2N at level minus 2n plus 1. This is a plan for the talk. First, we give some basic definitions, recall some basic definitions, and introduce the notation. In the second part, we give the summary of previous results on the representation theory of some simple affine VOAs. And then we consider our first example. It is affine vertex algebra associated to SL4 at level minus 5 halves. We will classify modules in the category O and in the Kazhdan-Lushly category. And we will prove that it is semi-simple, rigid braided tensor category. And then we extend these results to SL2N at level minus 2n plus 1 halves. So this is a plan for the talk. Okay, and now we give some basic definitions on affine Lie algebras. So we start with G, finite-dimensional simple Lie algebra over a field of complex numbers with non-degenerate symmetric bilinear form on G. And then affine Lie algebra is as a vector space. It is defined as a tensor product of G with Laurent polynomial sim T in direct sum with one-dimensional vector space. This K is central element, and Lie algebra structure is given in usual way. Here, XM denotes the tensor product of X with M power of T. And about modules, for G hat module M, we say it is of level K if the central element K acts on M as a multiplication with scalar K. So this is affine Lie algebra, G hat, and now notation of affine vertex operator algebra. We consider levels K which are non-critical, so they are not equal to minus dual Coxeter number, and universal affine VOA we denote by VKG. As a model for affine Lie algebra, we have isomorphism with this induced model. And this VKG contains unique maximal ideals, so there is a unique simple quotient, and we denoted it by LKG. So VKG universal, LKG simple. And now modules by VK lambda, we denote the generalized Verma module for affine Lie algebra of level K induced from the reducible highest weight module for Lie algebra G of highest weight lambda. And this VKG or VK lambda also contains a unique maximal submodule. So there is a simple quotient. We denoted it by LK lambda. So it is a simple module of level K and G highest weight lambda. And we are interested in the representation theory of LKG. Why most of vertex algebras could be constructed by simple affine VOAs via tensor products, extensions, orbifolds, and Hamiltonian reductions for some nilpotent elements. So it is important to understand the representation theory of LKG. And the problem is that for general Lie algebra G and level K, it is a wide open problem. So we give the summary of previous results. First, there were results for non-negative integer levels obtained by Frankel-Zhu and Lee. They proved that LKG modules, the category of LKG modules graded by non-negative integer numbers is semi-simple. We say that these LKG, these algebras LKG are rational. And then next results are obtained at so-called admissible levels. Dražen and Milas and Douglas Mason studied the SL2 case at admissible levels, and then Ozan Pasha studied some cases of type B and type P. Type B at a certain half integer levels, and then minus 1/2, and then I mean in their papers they used the explicit formula for the singular vectors and the Zhu theory, and it was hard to use these methods in general. And Arakawa proved the general result. He used some characteristic varieties and some general results from affine Lie algebras and reduction to the SL2 case. So the general result is the following. So the category of LKG modules, which are in the category O as the modules for affine Lie algebras, is semi-simple. So we say that we have a rationality in the category O. So in the category O here, we have infinitely many reducible modules. And this category is semi-simple. And beyond the admissible levels, there are not much known results. There are some results on negative integer levels because they appear in various contexts. We have negative integer levels which appear in free-field realizations of certain simple affine theories. Then they appear in the context of affine vertex algebras associated to the line exceptional series. And we have negative integer levels as collapsing levels for minimal affine W-algebras. So okay. Okay, and the problem beyond the admissible levels is that there is not much some technology which we can apply in general. So it is natural to restrict to smaller category, the smallest one, and but it is very important, Kazan-Lushri category of ordinary models. So this KG is semi-simple for generic levels K, and for K admissible, it is semi-simple. And then by Thomas, Huang, and Yang, it is proved that for K admissible, this KG is a Brady tensor category, and in most cases also the rigidity is proven. But this KG could be semi-simple also in the cases when K is not admissible. For example, it is proved that KLK is semi-simple when K is a collapsing level for a minimal W algebra, which means that simple minimal W algebra is isomorphic to its affine subalgebra, and also KLKG is semi-simple when the minimal affine W algebra is rational. So we have semi-simplicity here, and by Thomas and Young, at these levels, it is constructed a vertex tensor category. So that is the case when K is a collapsing level for minimal W algebra. But also there is a notion of collapsing level for non-minimal W algebra. And properties of quantum Hamiltonian reduction functor for non-minimal nilpotent element are not very well understood. So it's so at the moment we can only conjecture that we will have semi-simplicity at collapsing levels for non-minimal W algebras. And we will see that our case of SL4 at level -5/2 is one example of collapsing level for certain non-minimal W algebra. Okay, so it's very hard to consider all non-admissible levels. So we restrict to type A, G, SLN, and level K, which are in some way close to admissible. So in type A, we know that level K is admissible if K plus N is equal to P over Q, where P and Q are coprime and P greater or equal to N. And our levels close to admissible, we call them almost admissible, and those levels are of the form -n plus n minus 1 over Q, where n minus 1 and Q are coprime. So this P in admissible case is greater or equal to N, and in our case, we take this P to be one less, so n minus 1. And for such example, we obtain if we take Q1, then K is -1 for any N. So this is V minus 1 SLN. And if we take Q2, we obtain K minus N plus 1/2 for N even. It is almost admissible. And our case of SL4 at -5/2, it is first such a half integer level, which we obtain if we take N4. So here for this half integer, almost admissible levels, we expect to obtain similar results as in the case of level -1. So first we will recall the results on level SL4 at level -1. It was treated in the following way. So first, Trajan and Rosen determined the explicit formula for the singular vector in universal, this affine vertex algebra, and using that explicit formula in the Jou theory, they classified the reducible modules in the category O. They proved that this category is not semi-simple, and they found infinitely many irreducible modules. Very hard problem was to prove that this singular vector generates the maximal ideal. And it was very hard to prove that using just affine vertex algebras, but it was possible to prove that using theory of W algebras. So Arakawa and Moreau, they used minimal W algebras, actually minimal quantum Hamiltonian reduction functor, to prove that this singular vector generates the maximal ideal here. So this simple L minus 1 SL4 is the quotient of universal by one singular vector. And they also proved that the simple minimal W-algebra is isomorphic to Heisenberg of rank 1. So this level K minus 1 is collapsing. And this was also proved by Dražen, Katz, Monserrati, Freire, Papi, and Perche in their paper on collapsing levels. And in that paper, they also proved that Kazan-Lushty category in this case is semi-simple. And then by Kreutzig and Young, it is proved that this category is also rigid-braided tensor category. So we now want to prove these similar results in the case of SL4 at level minus 5 halves. So as I said, it is a new example of non-admissible half-integer level. It is also very important because it appears in conformal embedding. It is proved by Dražen, Katz, Monserrati, Freire, Papi, and Perche that for any n, both even and odd, at level minus n plus 1 halves, there is a conformal embedding of LK SLN times Heisenberg into LK SL n plus 1. But only for n even, this LK SL n plus 1 is admissible. And we will use that fact later. Okay, so now our understanding of this case SL4 at level minus 5 halves, we start with determining the explicit formula for the singular vector in universal V minus 5 halves SL4. We found the explicit formula for the singular vector of conformal weight 4 and G weight 2 omega 2, which is alpha 1 plus 2 alpha 2 plus alpha 3. Explicit formula is very complicated. It would take 3 or 4 slides. So I put here just some terms, and the remaining terms can be found in our first reference paper. Okay, but now when we have this singular vector, we consider its associated quotient, and we denote it by L tilde. First, we notice that we have an automorphism of this L tilde because we start with sigma automorphism of the Dynkin diagram of SL4, which interchanges the weights alpha 1 and alpha 3. It is lifted to the automorphism of universal vertex algebra, and it is easily to check using this explicit formula that it fixes singular vector V. So sigma induces the automorphism of L tilde, and this automorphism sigma will be used later, I will mention it. Okay, now when we have this singular vector, we are able to classify reducible modules for this quotient L tilde in the category O. So we have that complete list of reducible modules in the category O is given by this set. So we see that the highest weights of these modules are parameterized as a union of 16 lines. We have infinitely many modules, and the classification is obtained using Joute theory. So we obtain the formula for the image of the singular vector in Joule algebra, and then by solving a certain system of polynomial equations, we obtain these classifications. Zeros of that system are exactly these highest weights. And now from this classification, we see that these weights are dominant integral only in the case mu1 and mu2 for t non-negative integer number. So we have a classification in the category of ordinary modules. So highest weights.
Ivana,
yes?
Sorry, I have a question. Could you go back?
Yeah.
Oh, or maybe in this slide. The reason why you're putting a tilde is because you don't know that this is the irreducible yet. Is that right? You still need to show that the singular vector generates the maximal?
At the moment, we don't know that this L tilde is simple.
L. Okay,
Yeah.
thank you.
Yeah, so this is only, the moment this is a classification for the models in the category O and for ordinary models for this L tilde, not a simple. And our next goal is, our next goal is to prove the simplicity of this quotient. And the case -1 was treated by minimal W-algebra, and it turns out that in this case we cannot use minimal W-algebra. But we can use a subregular. So we start with F subregular nilpotent element, and x omega 1, omega 2 plus omega 3 semi-simple element, which defines a good grading of SL4 with respect to this F. And then by quantum Hamiltonian reduction factor, we construct universal W-algebra at level -5 halves. We know it is strongly generated by 5 elements, J, Virasoro, L bar, W, G plus, and G minus, and we have their conformal weights 1, 2, 3, 1, and 3 respectively. And we need the OP formulas for these generators, and are presented by Thomas Kreutzig and Andrew Lenshaw. Okay, and now we prove for this subregular W-algebra that level K is collapsing, which means that the simple quotient, its simple quotient is isomorphic to Heisenberg vertex algebra generated by this vector J. Okay, so that's the first important thing, and another important step in the proving the maximality of ideal generated by this singular vector V is the following. So we prove this lemma, which says that the image of the singular vector V in W algebra coincides with the vector G plus. And then we proved, so using this theorem and lemma, we prove this proposition, which says that both L tilde and simple L are mapped to Heisenberg vertex algebra using this subregular functor. But still, we weren't able to conclude that this L tilde is simple. And the problem is that the properties of a subregular functor are not presented so explicitly as in the case of the minimal reduction. So if we assume that we have some other singular vector, we didn't know is it mapped to 0 or not to 0. In the case of minimal reduction, in the case -1, G highest weights of models were also an omega 1 and then omega 3. But in the minimal case, we have a condition of weights that minimal reduction maps model to non-zero if and only if K lambda 0 plus lambda on co-root of alpha 0 is not non-negative integer number. And in the subregular case, we don't have such easy condition. But we proved the following. So we proved that for any positive integer number, modules of highest G weight and omega 3 are mapped to non-zero, and any highest weight of G weight, any highest weight module of G weight and omega 1 is mapped to 0. So here we have half of modules which are mapped to 0 and half of modules which are mapped to non-zero. And the proof of this theorem was very complicated. First, we need to have singular vectors in generalized Verma modules of G weight I omega n omega 1 and n omega 3. These formulas are also very complicated as the formula for the singular vector. but then we managed to obtain the description of these submodels and construct universal models for L tilde. Universal in the sense that any model, ordinary models for L tilde is a quotient of M bar. And for these models M bar, we proved the vanishing and non-vanishing of this subregular functor. So this is a very important step in our proof of maximality of ideal, and it was very complicated to obtain this result. But now we are able to prove this. So our singular vector V generates the maximal ideal in universal VI, so its associated quotient is simple. So that's the first claim. It is proved, now it is almost obvious, because if we assume that we have some other singular vector from the classification in KLK, we know that it is of G weight n omega 1 or n omega 3, but using automorphism sigma, we can assume that is of G weight n omega 3, and then we use property P, so it is mapped to something non-zero, and then we use exactness of this subregular functor. This subregular functor, it is in general not exact, but it is exact in the category of in KLK. So this is the first claim, and using similar methods, we prove that any highest way model in KLK is irreducible. And then using the result of Drashenkat, Maserati, Clara, Papi, and Ferchet, we obtained that KLK is semi-simple. So in the case of DSL4 at level minus 5 halves, we have that this category is semi-simple, and we have the description of the maximal idea. But we want to say something more about this KLK. We want to prove the existence of rigid braided tensor category. And to do that, we exploit conformal embedding. So we already mentioned that there is a conformal embedding, and we have the following the composition of LK, SL, and plus 1 as a model for this subalgebra. In the decomposition, we see that we have these models for LK, SLM here and here, and we have these models for Heisenberg. And to the end, through the rest of the talk, we use the following notation for irreducible models in KLK. These models of high G weight I omega 1 we denote by UI, and these models of G weight I omega 2n minus 1 we denote by U minus I n. And now if we consider SL4 at level minus 5 halves, we see that all of the models appearing in the decomposition are exactly the models from KLK. And we will use that to prove the following. So we have the fusion rules. So using this decomposition and standard fusion rule arguments, we prove that these models for SL4 are simple currents with these fusion rules, which means that dimension of vector space of intertwining operators of this type is equal to 1 when k is equal I plus j and 0 otherwise. So we write this, and again using this conformal embedding and the fact that all of the models from KLK are exactly the models appearing in the decomposition, we proved that exactly the same, using exactly the same methods as Kreutzig and Young in their paper on level -1, we proved that this category is a rigid braided tensor category, and this fusion our fusion rules gives also the fusion rules in vertex tensor category setting. Okay, so this is our first example. SL4 at level -5 We have maximal ideal, and we have the semi-simplicity and the existence of rigid braided tensor category on the Kazan-Luszczyk category of ordinary models. And next, we want to generalize these results from this corollary to the whole series KLK SL2n for any n greater or equal to at level k -2n + 1/2. And the problem is the following. In our first case, we use very complicated formulas for the singular vectors in universal affine BOA and in the generalized Verma models. We use the W-algebra, we use the OPs, so it is very hard to generalize these methods to the other cases. So for other cases, we need a different approach. And we will use a tensor category approach, which is used by Thomas McRae and Young. Their approach can be used to conformal embeddings from paper of Dražen, Kacmos, Radi, Freire, Papi, and Pache. And we expect that the category KLK of ordinary models for all of these sub-algebras appearing in the composition will have the structure of rigid braided tensor category. So in particular, we expect that we can apply that to the KLK SLN for any k minus n plus 1/2. So we expect that this is also a rigid tensor category, but only for n even, this level k is admissible. So only for even n, we expect to get a similar vertex tensor category structure as in the case SL4 at level -5/2. The case when n is odd, it's much more complicated because not all of the models from KLK appear in the decomposition. So when n is even, we will see that all of the models from KLK are simple currents and they appear in the decomposition. And when n is odd, that's not the case. So we will consider the case when n is even, and the motivation to look at this level is also the fact that these levels are collapsing for W-algebras of a certain hook type. And it is proved by Dražen, Radi, Freire, Papi, and Pache. So these levels are collapsing also, they're collapsing for W-algebras, both for n even and odd. Okay, so this is our main theorem. So for KLK SLM is semi-simple rigid braided tensor category for all even m greater or equal 4 at level k minus n plus 1/2. And models in KLK SLM are simple currents, and all of them appear in the decomposition of previously mentioned conformal embedding. And now we will discuss the proof. So the argument for in the proof is induction for m, and our base case is SL4 at level -5/2, which we just proved. And to prove the step of the induction, we need to recall the results on singlet, which was studied by Dražen, Milas, and Kreutzig, McRae, and Young. So we consider the category of all C1 cofinite models for singlet, we denoted by OM2. It is a rigid braided tensor category, and we have the we have the list, complete list of inequivalent simple models. They consist of two series, which we call typical and atypical. And in our context, we consider atypical models for singlet. We denote them by MI. These models, MI, are simple current in this category, and we have the following fusion rules. Next, we will need some calculation on conformal weights. So let me just mention here that the conformal weight of top level of this atypical model MI is equal to absolute value of I times I plus 1/2. Okay, so this is singlet. And now we do the following. So we assume that KLK SLM is a braided tensor category for some M. And then we do this extension of this algebra by simple currents. And then using the fact that we have tensor categories here, and here, we know that this simple current extension is simple VOA, and we know the generators, and then by using very strong uniqueness theorems for simple VOAs of this type, we conclude that it is exactly W-algebra of level K, minimal W-algebra of level K associated to SL m plus 2. So from SLM at level K, we obtain W-algebra associated to SL m plus 2 K minus 1. So our first case was SL4 at 11 minus 5/2, and now we constructed minimal W-algebra at level minus 7/2, SL6, and so on. So these are atypical models for singlet, and this is a Fock model for the Heisenberg. This is L minus M over M plus 2 rescaled field. Okay, so now we have this simple current extension, and then the theory of vertex algebra extensions allows us to study ordinary models for this minimal W-algebra. And we know that any ordinary model for this minimal W-algebra has to be induced from the model for this algebra of the form UIN times F some A, and model for singlet, typical or atypical. Okay, so we classify the ordinary models for this minimal W-algebra, but we want to conclude which of them can be constructed using quantum Hamiltonian reduction functor of the models from KL K-1 SL m plus 2. And we proved by calculation some conformal weights and all of these assumptions that if we take a simple model in KL K-1 SL m plus 2, then its Hamiltonian reduction functor is isomorphic to this induced model. So we need to have a typical model And we have this condition on A and B. So B is equal to m plus 2 over m A, and it needs to be integer. Okay, so now we know which modules for minimal W algebra are obtained using quantum Hamiltonian induction functor on modules in KL k-1 SL m plus 2. And now, using that and using the composition of conformal embedding, we proved that KL k-1 SL m plus 2 is semi-simple rigid braided tensor category, and we proved that we obtained the classification of irreducible modules. So here, irreducible modules are of G weight I omega 1 and I omega m plus 1. Okay, so this is a theorem with how to say with all of these together. So we have a classification of irreducible modules in KLK SL2N. We have the fusion rules. This category is semi-simple rigid braided tensor category. And in every step, we have that this simple current extension is isomorphic to this minimal W algebra. And let me just mention that this theorem gives a whole family of new examples of semi-simple KLKG at collapsing levels for non-minimal W algebras. So this is a whole series. And just a short note that this decomposition can be obtained in the second way. So this is a second approach. We take S beta gamma vertex algebra, also called well vertex algebra, and then this minimal W algebra is isomorphic to commutant of certain Heisenberg into this tensor product. So this one is admissible, and this is a tensor product with beta gamma. And using the decomposition, using the decomposition of this admissible as a module for our LK-1 SLM plus 2 and Heisenberg, we obtain this decomposition. And the good thing in this approach is that it holds for any M, even and odd. And this one is only for M even. Okay, that's all.
Thank you so much, Ivana. Any questions for Ivana? Please feel free to unmute yourself and ask. I guess I have a question. So this last theorem that you mentioned gives you this decomposition, but maybe doesn't help you describe KL, like the Gaussian-Lustig category in this case. Is that right?
Yeah.
I see. Do you have hopes of still describing the Gaussian-Lustig category for the odd dimensions?
You mean the case when this?
Yeah.
It's very complicated because I mean I don't have any idea except as a first step calculation a singular vector. But it is very complicated. In this case of SL4, it was already very complicated, and in high ranks, it's probably terrible.
And the problem, you said the problem was that not all irreducibles were realized in some decomposition? I forgot, could you mention that again? Sorry, I forgot what that decomposition was.
Okay, so what is this? Just okay, so we have these modules,
Mhm.
but for example, if we take M5, we have L minus 3 SL5 tensor Heisenberg into L minus 3 SL6. But this one is not admissible. And here we have a lot of models in KLK. I think that all of them are M omega 3 for M.
I see.
And using them, we can construct the models in KLK for this one, which are not disappearing in the composition. And in the proving that we have a tensor category structure, it is very important to strongly use that all of the models are this one. So that's the problem in the odd case.
Thank you. Mhm. Let me stop the recording.